Hello guys and welcome to a new episode of Leubniz Lecture. Today I want to talk about the data structure list, especially about linked lists and the different types of linked lists that we know. Additionally, I want to show you how to implement your own linked list using Java. So let's do not waste any time. Let's head over to our presentation for today. Good. So before we can talk about the data structure list, we have to recap the data structure array. There is some basic knowledge that you should be aware of when it comes to the data structure array. So first of all, the array has the property that whenever you define an array, you also have to define the size, and this size is fixed. So you cannot change the size of the array, for example, when programming C or Java. Additionally, the elements inside the array have to be of the same data type. So you cannot, for example, store elements of the type string and int in the same array. So this is not possible. Because of this predefined size, we have a very big advantage using arrays. All the elements are stored one after each other in memory without any gap in between. And this leads to the very cool and nice way of accessing elements inside the array by just using an index. So the array itself just knows the start address, so wherever the first element of the array is. And by adding the index to the start address, we can access the different elements in there. So this is on the one hand side a very big advantage, but can be very dangerous, for example, in C if you do not take care of how you handle all the accesses there. Good. So what about inserting and deleting elements from an array? So when we want to insert an element at some defined index, this can be very difficult because first of all, we have to change the size of the array, and this is not possible. Okay, what can we do? We can just create a new array, which is just one element larger than the old one, then shift all the elements back by one, and then insert the new element at the defined position. Very hard procedure to just insert a new element. So let's see how the deletion works. So once again, we want to delete some element at a defined index. So what we do is we move all the elements to the front because we cannot produce a gap or an empty element somehow. That's not possible. So move all elements to the front. And if it's needed, we even have to decrease the size of the array, which means once again, creating a new array, which is a little bit smaller. So usually one element smaller than the old one, and copy everything there. What does this do? It creates us a lot of array element movements, and this is usually something we want to avoid here. And that's a very big difference when it comes to the data structure of a list. So let's see. The data structure of a list holds elements. So this is the same as the array also does. So there is no big difference. But when it comes to saving the elements in memory, there is a very big difference, because the data structure list spreads its element in the whole memory. So wherever there is some place for an element with a special size, we place it there. So they are not just one after the other in memory, they're just somewhere spread. So one thing that's not possible anymore is accessing elements using the index. So we have to come up with another idea of how to link the elements. That's already where the linked list comes from. Just to clarify one important term, so every list element that we talk about is called a node. Good. So in this drawing here, we see three elements. So we see three nodes. Let me just get the laser points here. Okay, so we see three nodes with element 1, element 2, and element 3. And each of these elements hold some data here. Data, whatever the data may be. Now, we somehow have to link the elements with each other, and this is done by using pointers. So element 1 consists of some data, so this node has some data, and also a pointer to the next element. In our case, it's element 2. Element 2 once again has data and a pointer to the next element. That's element 3. Element 3 also has data, but oh wait, no pointer here. Okay, that makes sense because element 3 is the last element, so why should there be a pointer? And the very nice solution is to just set the pointer to null here because it's pointing nowhere. Another important term is the first element, the first node is called the head. So this is wherever we start. So whenever searching for an element, whenever inserting, deleting, or whatever, we always start from the head because this is our reference, this is what we know, and then we have to handle through all the other elements to somehow come to the next element there. So, okay, let's head over to Java and find out how we can implement our own linked list. Therefore, I just created a demo here using IntelliJ, so you can use whatever IDE you want. And the first thing that we have to do is we have to create a class that represents our element, so our node. And as we saw this before, the node has two instance variables there. So the first instance variable is the data. So we define that the data is always some integer here. And additionally, what we have is a pointer to the next element. So in our case, we do not use a pointer here, but we just use a variable of the type node here. And this node is always the next node then, or a reference to the next node here. Good. So to access the data and the next and the node, we have to insert and create some getter and setter methods here. So let's just generate them, and we're done with our node here. Good. So to use our node and to somehow create an example, I want to create another class called main. And in there, in this class main, we need one node. We need our head node, and I call our head node list. And at the beginning, this head node is null because we have no elements at the beginning. So this has to be null here. Good. So that's it already. Let's just create our main method here, where we create a new object of our class main here. And I think that's it already. So this is our basic structure. So you may pause the video here to just reproduce what I did here. What I did is I created a node. So one node represents one element with the data and a reference to the next element with the getter and setter methods that we need to access them. And I just created some main class here with a main method to somehow produce an example and to hold all our methods that we're going to create. Okay. So let's head back to our presentation here and let's see how we can output our list. So this is the setup that we have right now. So we have our head element, which is called list here. And we want to create a list that has 4 nodes. First node with the data of 2, second 5, the third 11, and the fourth 24. Good. The question is, how can we print all the elements? Okay, that's not that difficult. We start with our head node because this is what we know. Then we go to the next one, we print the 5. We go to the next one, we print the 11. We go to the next one, we print the 24. And as soon as there is no next element or a node because the pointer or the reference is null, we are done. So let's try to somehow implement a method that prints all the data of our elements. Let's see. Let's head back to our main class here and let's just create a method called print list. I think that should be fine to do a print list here in that way. Good. So first of all, what we need is some variable that we call the actual element or the actual node. This is the element that we're currently looking at. One thing that we have to check is if the list is null, we do not want to do anything. So only if the list is not equal to null, we want to go on because otherwise there is nothing to print. So first of all, the actual node. So we set the actual node to be a reference to our head, which is list. And then once again, while the actual node is not equal to null, we print all the elements. So we do something like system out format. And what we do here is, let's do a % for D. And what we print is actual node dot get data, because this is the data of the current node that we want to print. Good. That's it nearly, because we just have to do one more thing, because we have to jump to the next node, to the next element. And this is done by just saying actual node is equal to actual node dot get next. So this means we are now checking if the list is not null. If the list is not null, we are grabbing our actual node. And then until the actual node is not equal to null, we print the data and we move forward to the next element. Okay. And remember, our last node, which was element 3 or element 4 in our case right now, had a null reference to the next node. So this is where we would stop then. Good. So in the same way, it should be possible to create a method that returns the number of elements that we have in our list. So let's create a method here. So get number of elements here. Good. So we have our number of elements method. So we have our number. This number is equal to 0. And now, once again, what we need is our actual node, and the actual node is a reference to our list. So this is where we want to start. So, and the procedure is kind of the same as before. So as long as the actual node is not equal to null, we increase our number by 1, and we say actual node is equal to actual node dot get next. Okay, looks good. So let's just head down here to our main, because at the end I want to do two things. I want to print something to the console. I want to say elements in the list. And before that, I want to call the method get number of elements. And after this, I want to print all the elements. Okay. I just saw that I forgot to return the number here. Otherwise, this won't work. Good. So let's run this. And usually what we would expect, as our list is still null and we're not inserting anything here, we expect to get the output 0 elements in the list. And there is no output because there are no elements there yet. Good. So I think we are ready to go on to the next part. And the next part is talking about how to insert something into a linked list. So we have our list here. This is what we want to produce, 2, 5, 11, 24, our nodes. And this is our new node, 9. We want to insert 9 at that position here. And that would be index 2, because this is index 0, this is index 1, and this is index 2. And we want to insert it here, so in between 5 and 11. So you already have an idea of how we can do this. That's easier than you think. We just have to rearrange the pointers. So the element, or the element with the data 5 is now pointing to the new element, and the new element, the new node, is pointing to the node with the data 11. Everything stays as it is. And that's how easy we can insert something. So that's the very big advantage of a list. The elements are spread over the memory. They are somewhere stored, and we can just change the pointers, the references here, to insert a new element to the list. So that's how easy that is. And to see this in practice, let's do the implementation of a function that's doing exactly this. So we create a function that returns the node, so that returns the new node that we insert, and we call it insert add. So first of all, we need some index, and then we need some data that we want to insert here. So we need the actual node here, and what we need to is the new node. So these are the two elements that we have. So first of all, we have to create our new node. So we say new node equals new node. Then we set our data. So we say set data equals data. And what about our next element? We don't know what our next node will be yet. So just write null here. So we set it to null. Good. So there are two cases that we have to differentiate. So the first case would be to insert the element at the beginning, because this is slightly different from all the other cases. So if we remember the drawing that we had before, if we want to insert something at the beginning, this means if the index that was parsed is equal to 0, that's very easy, because the new element, the new node here, is just the first one. So the next one would be the first one, which is currently our list, and our list will be the new node. So that's the easiest way here. We say, okay, we want to insert our new element at the very beginning, which means the next element will be the current first element, and then the first element is the new node again. So we have to update our head element here. So otherwise, if we want to insert something somewhere in the middle, we need a helping variable I here, and we can say our actual node is equal to the head to our list. So what we have to do is we have to find the element before the new element right now. So we have to somehow find the element that's one index before the one where we want to index it. So as long as I is smaller than index minus 1, we want the actual node to be actual node.getNext. So what this does is it just goes through the list, so handles from one node to the other until we reach the element before the position where we want to insert our new node. So we increase our I at that position here. And then after the while, we just have to update our nodes. So our new node has a set next now, because the next of our new node is what the actual node.next currently is. And the actual node.next is now the new node. So the actual node is the node one position before the index where we want to insert something. This means the actual, which means that the successor of the actual node is the new node. That's why we set next new node here. And the successor of the new node is where the actual node was pointing before. So what next of the actual node was before. And that's it already. So we return our new node, and that should it be. Okay, guys, I think we are ready to try this. We have no elements in our list yet. So let's insert at index 0 and let's insert 24 here. If we run this and if we are lucky, we should see that there is now one element in our list. And I just want to set up the basic structure that we have in the slides. So we need to have 11 here, we need to have 5 here, and we need to have 2 here. So this is our current list now. So if you have a look, we have 2, 5, 11, 24, and this is also what we see here. So we have 2, 5, 11, and 24. Good. So now let's check if this works. So we said that we want to insert an element at the index 2, and the element that we want to insert is 9. So let's see if this works. And if we did the implementation correct, we see we have 2, we have 5, and at the index 2, we have 9, then 11 and 24. So nothing else changes, and it works just as we expect it to. Great. Okay. So I think you might already know what's the next topic to come up. We want to delete an element. And the deletion of an element is even easier, because if we want to delete, for example, here the element at index 1, what we do is we just set the reference for the element, for the next element of the one before, to be the one after. So we just skip the one in between, and that's it. Okay, so let's see how this works in practice. Let's head back to our program again, and let's write our method here. So it's public void delete at. We have our index, and let's start here. So we have our actual node once again, which is our list. And as you might remember, we also need the previous node now, because the previous node is the one that we want to where we want to change the pointer to skip one element. So when can we delete an element? We can delete an element whenever the index is greater or equal to 0, and whenever the index is smaller as get number of elements. So this is a valid index, and if something is not valid there, we just write deletion not possible. Okay, so that's just some kind of security mechanism there. Once again, we have to differentiate two different cases. So if the index is 0, which means we want to delete the very first element, that's very easy. We just say our head element. So we want to get rid of our head element. So our new head element is the actual node.get next, because the actual node is our head element, and we set the new head element to be just the actual one dot next, which is the reference to the next one. Good. So the other way around here, so if it's not the index 0, we have to check on our previous node, which is list, and we have to define our actual node to be list.get next. And now what we do is we once again go to the element that we want to delete. So we say, so we create a for loop here where we say index I equals 1. As long as I is smaller than the index, we want to be in that loop. And what we do is we say that our previous element is the actual node. So we just copy that one here, and the actual node is equal to the actual node.get next. So this is just going on here. Good. And what we can see here and what we get here is that the actual node now is the one that needs to be deleted, and the previous node is the one that's one before the actual one. So remember, we needed that one before here. Let's just recap that here again. So this is the previous node, this is the actual node, okay? Because for the previous node, we have to change the reference, the pointer, to skip the actual one, and to know where to point to, we have to use the actual one, okay? That's why we need both of these references here. And then we can just say previous node dot set next is equal to actual node dot get next. So we skip the actual node here. After this is done, we can get rid of the actual node. So in Java, we just set this to null, which means that the garbage collector can somehow grab it. Okay, and that's it already. That's our delete function, or method in that case here. So let's try it. We say main.delete at, and we choose the index 3. So with the current output, what do we expect? We have index 0, index 1, index 2, index 3. So we expect that we get rid of the 11. So the output should be 25924. So let's see if this works. Okay, so it worked fine. We have 259 and 24. Great. So that's it. We implemented our own list just right now. So I think that's great. That's fun. Cool. So If you want to practice further, there are some different ways you can do so. And I think the best way is to just implement some more functions, for example, or methods here. For example, what you can do is you can create a method that deletes an element not at an index, but that deletes an element or all elements with special data in it. You can create a method that deletes all the elements. You can create a method that inserts something at the end of the list, or that inserts something at the beginning. You can create a method that deletes something at the beginning or deletes something at the end. So all the things, so inserting and deleting something at the beginning, we already covered that here, but let's try to create a method that inserts and deletes at the end. So this might be a good exercise here to practice all of this stuff. Okay, so let's head back here. Yeah, there are two types that I want to talk about shortly. So this is the doubly linked list. What does this mean? So we had a single linked list before, which means that we had one pointer pointing from one node to the other. With the doubly linked list, we have two pointers. So we have one pointer pointing to the next element always, as we see it here. And every element also has a pointer pointing back. So we have one pointer to the successor of the element and always one pointer to the predecessor of the element. So this is the doubly linked list. So we have two references every time, which means that the end of the list has a null reference to the next element because there is none. And the first, so the head element, the head node, has a null reference to the predecessor because there is no predecessor. That's a doubly linked list. And there is so when inserting something in a doubly linked list, we have to change 4 references. So if we want to insert or delete something, whatever, so it's the same procedure as with the single linked list. The difference just is that we have to change 4 references, 4 pointers here. There is one more type of a linked list, and that's a circular linked list. And with the circular linked list, there is just one addition, and this addition is that the last element has a successor, and the successor is the first element, and the first element has a predecessor, and the predecessor of the first element is the last element. So this is circular list you can never go around. This is very tricky when it comes to iterating through a circular list, because you have to find a way of finding out when you reach the end or when you reach the begin again, because otherwise you will end up in a loop that goes on forever here, and this is nothing that we want to have. Okay, guys, so this is already the end of this lecture about linked list, about the different types, and we also implemented our own linked list. I want you to practice this, so if you want to understand this a little bit better, try to implement the methods that I asked you to do so, and otherwise, I just want to say thank you for listening. Thank you for visiting my channel again. If you like this video, just give it a like or subscribe my channel if you want to see more of my lectures. Thank you and see you next time. Bye.